Okay, Assalamualaikum and good morning, everyone.
Good morning, sir.
Okay, so today we will continue with lecture number 3B. So last week we have learned about motion and how we can use um, the equation of motion in terms of some function to describe the motion of a particles in the body. So today we will look at how from the motion we can derive, we can determine the different terms, okay, or different physical quantities that represent the strain of the materials. So in this topic, there will be a lot of new terms to you, and there are some derivation, but in exam there will be no derivation required. But all of the calculation will involve the formula that are given in the lecture notes. Okay. So in this topic, we are going to look at a new terms called deformation gradient. So at the end of this lecture, you will be able to understand the concept of deformation gradient and understand the different definitions of strain tensors. Okay, so basically we are going to look at strain. So in solid mechanics, in SOM 1, SOM 2, you probably have encountered the term strain. Okay, so strain is basically the change in length divided by original length. Okay, so that's basically the basic definition of strain. But because of deformation of a body, there will be a lot of definition of strains, okay, depending on the different point of view or configurations. Okay, so in previous lecture, we have learned about motion that describes the motion of individual points in a body. However, the motion that we have learned last week uh, does not tell us whether the body has changed in shape or deformed. Okay, we know that the particle is moving, okay, moving to a new position, but we didn't quantify whether the body has changed in shape or whether it's uh, deformed or whether it just uh, either rolling or moving in translational motion. So the shape will change if we can measure the material points movement in relation or in relative to one another. So for example, if the body moves rigidly, so if the body undergo rigid motion or doesn't involve change in shape, then the distance between every point or every pair of points will remain the same. But if the body deforms or the body change in shape, then the distance between these points also changes. Okay. Hence, to quantify the deformation requires the study of the evolution of material-like elements. Okay, so we are going to look at the derivation of the terms deformation gradient. So let's consider a line PQ. So here PQ here, which is at the undeformed configuration or at original condition or original configuration. And this line PQ undergoes some motion, okay, motion chi here, and then change in shape. Okay, so the PQ, capital P and Q, now change in position and shape into a new line, small PQ. Okay, so there are some derivation here. So we end up with the length of the final PQ, small PQ, equals some term F times the original length, the X, okay, the original length of PQ. So the F here equals the identity matrix I plus del U over del x. Okay, u here is the displacement. So I plus del u del x or equals del x del small x over del big X. So F here is the deformation gradient tensor. Okay, so if you look at the definition here, d small x is the final length and d big X is the original length. So if you bring d big X to the other side, then F represent the change in length divided by original length. So it's something like strain quantity. Okay. So let's look at an example how to determine deformation gradient from this formula here. This formula, del small x over del big X. Okay, so basically we differentiate small x with respect to big X. So let's look at an example. So example 1, given the motion of a deformed object, so we have x1 equals t plus 1 squared x1 plus t x2. A small x2 equals t squared x1 plus t plus 1 x2. And then x3 equals x3 plus t times x3 squared. Okay, so the question asks you to find the deformation gradient f. So f equals del x small x over del big X. So the general formula is this in the bracket here. So when you find f, then there will be 9 components of f. Okay, it's a matrix. It's a tensor, 3 by 3 tensor. So the first column or the first row here is differentiate x1 with respect to x. Okay, x1, x2, and x3. Second row is differentiate small x2 with respect to x1, x2, and x3. And row number 3, differentiate x3 with respect to x1, x2, and x3, okay? Big X, okay? So I mixed up the small and big X. So I hope you understand the small and the big X, okay? So just from this equation, you just differentiate accordingly. Okay, so maybe at first you will find that differentiating this takes a longer time, okay? Because you have to differentiate 9 times, 9 kali. But as you try more example or exercise, you will find that actually differentiating this tak perlu tengok formula ni pun, okay? Boleh dia macam keluar sendiri, okay? So firstly, let's differentiate del small x1 over del big X1. So if you look at the first equation, so differentiate x1 over small x1 over big X1. Basically, you differentiate only this part here because x2 is considered a constant. So this becomes 0. So differentiate this, you get t plus 1 squared. Okay, so we differentiate about x, okay, with respect to x. So time t will become a constant. Okay, so that's why we get t plus 1 squared. Now we repeat the process but differentiate with respect to big X2. So big X2, then this portion here becomes 0. Then you only look at the second part of the equation. So differentiate this, you get t. And then the third one is del small x1 over del x3. So in the first equation, there is no x3. So the answer is 0. Okay, so similarly for the second row, x2. So look at the x2. And then with respect to big X1, so you get t squared. And then second one with respect to x2, you get t plus 1. And then the last one is with respect to x3. There is no x3, so you get 0. And then for the last row, you differentiate x3, small x3. So differentiate small x3 with respect to big X1. So no x1, you get 0. No x2, you get 0. And then x3, there is x3 here. So differentiate this part, you get 1. and then differentiate the second part here, you get 2t x3 squared, x3, sorry. Okay, so whenever a question asks you determine the deformation gradient, then this is the formula, okay? So let's try this exercise, okay? Given the deformation of an object, chi x equals this equation. So now the equation is arranged slightly different, okay, compared to the example. So the example, the equation is separated in terms of x1, small x2, and small x3. But you have to remember that motion is a vector, so it can also be written in vector form. So if you find this kind of motion in vector form, uh, it will be uh, good if you can separate them in component form. So you can write x1, small x1 equals 3.5 plus x1 plus 0.5 x2. And then x2 equals 4 plus x2. x3 equals big X3. Then here it's more, it's clearer how you can differentiate and find deformation gradient. So the deformation gradient equals, so the first part here, the first row is for small x1. So small x1, differentiate small x1 with respect to x1, big X1. So if you look at x1, there is no constant here. If you differentiate, it becomes 1. So this is 1. And second component is with respect to x2. So there's a constant here. You differentiate with respect to x2, you get 0.5. There is no x3, so 0. And then second row is x2. So you differentiate x2 with respect to big X1. There's no x1. And then with respect to x2, you get 1. And there is no x3, you get 0. And then lastly, for the third row, you differentiate small x3 with respect to x, big X. So there's no x1, no x2, and there is x3. You differentiate, you get 1. Okay, so you get this deformation gradient. Later on, we will see why we need deformation gradient and how to use deformation gradient in deriving other things or in obtaining other quantities. But for now, I hope you try this later, how to get this deformation gradient. Okay, so one of the important things about deformation gradient is the Jacobian of the motion. So what is Jacobian? So there are a lot of terms. So it's just name, okay? It's just name, but the definition, there will be no question like define Jacobian, define deformation gradient. So as we deform an object, it may locally compress or dilate, causing the density to vary with time. So let's say you have an object. So because we define the motion of an object using mathematics, sometimes when we calculate something, then we might get values that are not physically relevant or physically logic. Okay, so that's why we have this Jacobian. So the equation dx, the small x equals f d big X, represent the deformation gradient just now. So if f dx equals 0, by assuming the original length is not 0, you have the original length. So this implies that during deformation, the material length is reduced to 0, which is impossible. So what happens is that if you deform an object, then the object macam hilang, okay, gone, because there is no final length. Okay, so this can happen if you use mathematics, okay, to derive something. So you have to limit the calculation. Okay, so therefore, if we have f dx, or the final length, equals 0, then this also means that f is non-singular, and has an inverse. Okay, so f, the deformation gradient, has inverse, can be invertible, just like a matrix. Okay, matrix boleh dicari dia punya inverse. So for non-singular tensor, the determinant of the tensor must not equal 0. So ini this is the condition for finding inverse. Okay, I think I've explained this in lecture on matrix. So if you have inverse, then the determinant f tak boleh jadi kosong. Okay, kalau kosong, dia punya inverse tu akan jadi infinity. Okay, because if you want to find inverse, you need to 1 over determinant f. Okay, divide the determinant f. So the determinant cannot become 0. Okay, so the Jacobian of the motion is basically is this equation, the J, Jacobian J, equals the determinant of the deformation gradient. So this is important things that you need to remember. Jacobian is just the determinant of f. Okay, so from the Jacobian, we can determine the types of motion or the types of deformation. So firstly, the deformation, isochoric deformation. So isochoric deformation is the deformation in which the volume of the material is unchanged, tak berubah volume dia. Like if you throw a potato, like last week potato, dia punya volume still sama walaupun shape dia berubah. Okay, even though the shape change, but the volume remains the same. Okay, maybe dia tak compress lah. Okay, they just change in shape. So for a isochoric deformation, the Jacobian for the isochoric deformation, J equals 1. Okay, so this is important. If the question asks you determine whether the deformation is isochoric deformation, so you need to find the determinant, the Jacobian, and then make sure it's equals 1. If not equals 1, then dia bukan isochoric. If the deformation, the Jacobian equals 1, then the deformation is isochoric deformation. Okay, so maybe you will ask what happened if J equals negative, okay, less than 0. Okay, actually this can happen if we use mathematics, but in continuum mechanics, this tak wujud lah. Okay, it basically represent if you have Jacobian negative, when you compress a material, dia basically dia akan berubah bentuk, and then until get a point. So bila dia jadi satu titik ni, maksudnya Jacobian dia dah kosong dah, and then dia membesar balik, tapi membesar in like a mirror image way. Okay, tak tahu macam nak cakap. So this dari sini, this point onwards, dia tak logik lah. Okay, not logic. Okay, so usually the Jacobian won't be less than 0. But if we apply this in, let's say, finite element software, sometimes the software might calculate to get Jacobian less than 0. So you can set in software to ignore Jacobian equals 0. Okay, if you actually doing finite element simulation, because when the software get Jacobian equals 0, basically the mesh will be distorted. Okay, so maksudnya simulation tu dah salah. Okay, kena check balik ataupun make some changes in the mesh. Okay, so there are other deformation. We have homogeneous deformation. So homogeneous deformation occurs when the deformation of the body is the same for all the points in that body. So the deformation gradient does not depend on the reference position, but only depends on time. So this is deformation, homogeneous deformation. And lastly, rigid body motion. So a rigid body motion involves only rotation or translation, but no deformation. So rigid body motion is both isochoric and also homogeneous. So the deformation gradient for rigid body motion is orthogonal. So orthogonal, if you go back to lecture on matrix, so orthogonal ialah bila if you have matrix Q times its transpose equals identity. So if you have this, then Q is orthogonal matrix. Okay, so this is also important. Okay, the terms are orthogonal. Okay, so let's look at an example how to apply the Jacobian. Okay, so consider a deformation defined by this mapping or motion. This motion determine the conditions under which this motion is isochoric. Okay, for time positive time. Okay, so firstly we determine the deformation gradient. Okay, so you determine the deformation gradient using the formula for the deformation gradient, and then you get this matrix. And then after that, you determine the Jacobian. So Jacobian is just the determinant of this matrix. Okay, so how to find this determinant? So basically you tutup point ni and then darab silang. Okay, so you get E minus power of minus 80 times E power of minus 80. Okay, and then you repeat for the second column. So you have 0, so just plus 0 or minus 0. And then for the third column, so you have 0 here, then plus 0. Then you end up with E power of 2AT. Okay, so similar with this one. And then for isochoric deformation, we know that Jacobian equals 1. So when Jacobian equals 1, you get this equals 1. And then just find the value of A. Okay, so to get A, guna calculator boleh ataupun guna itulah pengetahuan in index number. So any index number power of 0, you get 1. Okay, so A equals 1 because time is always positive just now. So A equals 0. So for A equals 0, then the motion is the deformation is isochoric. Okay, pengiraan dalam soalan exam midterm dan final macam ni je. Okay, so try fahamkanlah. Alright. Okay, so that's about deformation gradient and Jacobian. So let's look at something else. Okay, so this is just some formula that not going to be used in this lecture, but going to be used in lecture maybe after midterm. Okay, or maybe after midterm. Okay, so the Jacobian J relates the current deformed volume to the original volume. Okay, so J also equals the change in final volume divided by the change in original volume. So the change in the surface area, so let's say if you have a small volume here, and then we want to determine the change in this surface area here after some deformation. Okay, mungkin dia berubah in area dia. So the change in the surface area on an element in the material depends on the outward unit normal vector. Okay, dia bergantung pada this vector normal to that surface. So dia punya formula dia this one. Okay, so not going to be used now. This is just introduced now. Okay, later on we will use this. Okay, not now. Okay, so ada exercise lah. Okay, so let's try do this exercise here. Okay, so the motion of a body is described by the mapping. So determine first the component of deformation gradient F and its inverse. So let's try first question. So from the motion, you can split them into three components first. If you find that this equation are confusing, so better separate them. So if you separate, you get this. Okay, so the deformation gradient is just differentiate first for the first row, differentiate x1 with respect to big X1, big X2, and big X3. So for the first element is differentiate small x1 over big X1. So you get 1. Second part is you get t squared. And lastly, you get 0. So similarly, for the second row, you get t squared here. You get 1 and 0. And lastly, this is 0, 0, and 1 because you differentiate with respect to big X3. Okay, later on, you can try this. All right. So you get this, then to find the inverse, because you have t squared, then kena calculate manually to find the inverse. So firstly, before you can find the inverse, you can find the determinant dulu. So the determinant, you get 1. Okay, just cross ni and cross multiply. And then repeat for the second column. You get t squared times t squared. And then lastly, for the third column, it's a 0 here. So just plus 0. So you end up with 1 minus t power of 4. So this is the determinant. And then to find the inverse, you need to find the matrix cofactor. Okay, so I hope you know how to do the inverse by yourself, okay? Because you need to go back to maths masa first year dulu lah. Saya pun tak ingat macam mana nak inverse kan. So matrix cofactor, so you get 1 minus t squared code, okay, 0 t square minus 1 0 0 0 1 minus t power of 4. And then the inverse is simply inverse equals 1 over determinant F times cofactor matrix F. Okay, so you get 1 over 1 minus t power 4. So just rewrite lah. Okay. Okay, so usually in exam probably kalau terkeluar soalan macam ni, payah sikit lah kena kira manual ataupun since it's online you can just use symbol lab, okay. So the second question is determine the components of displacement, velocity, and acceleration. Okay, so dia tak cakap in what configuration, okay, in Lagrangian or in Eulerian. So, but you can find both. Okay, so here I will only find the Lagrangian. Maybe later on you try to find the Eulerian velocity and acceleration. Okay, so for displacement, u it's equals small x minus big X. Okay, so this is from last week lecture. So small x minus big X. So you can find in components, u1 equals x1 minus big X1. So just rewrite small x1. So you get t squared x2. And then small small u2 is x2 minus big X2. And then lastly, for small u3, okay, so you get 0. Then to find the velocity, so small in Lagrangian, so velocity in Lagrangian is big V1. So you just differentiate the displacement with respect to time. So you get 2t x2. So for V2, big V2, you get 2t x1, and big V3 0. Then repeat for acceleration. So differentiate this with respect to time. You get 2x2. And then A2, differentiate V2 over time. You get 2x1. And lastly, A3 is 0. Okay. And then to get this is in Lagrangian. So to get in Eulerian, the small v1, v2, and v3, and small a1, a2, and a3, what you have to do is you just substitute x2, x1 here using the inverse of the original motion here. So you need to find the inverse of this matrix here. So if you rewrite this in matrix form, okay, so if you rewrite in matrix form, then this equation represent the small x, okay, small x. So to find the Eulerian velocity and acceleration, first you need to find big X, big X2, big X1, big X2, and big X3. Okay, equals, so you inverse this, okay, find the inverse. And then x1, x2, x3. So again, this inverse, you can just use the inverse from this, okay, from the deformation gradient inverse. It's the same, okay. And then substitute into the velocity to get the Eulerian velocity and acceleration. You can try later and see whether you get this or not, okay. Then question C, the position x1, x2, x3 of the particle in undeformed configuration that occupies the position x1, small x1, small x2, small x3, 9, 6, and 1 at time t equals 2 in the deformed configuration. So here the question is a bit tricky. So the question gives you the position at deformed configuration at certain time. So the question asks you to find the original position of that particle. So what you have to do is you just substitute this into the motion equation. Okay, so you get 9 equals x1 plus, so time is 2. So second one is 6 equals x2 plus 4x1. And lastly, 1 equals x3. So what you need to do is you have to solve this equation and find x1, big x1, big x2, and big x3, which is the original position. Okay. So try solve this later by yourself. And then question D, the location at time t equals to of the particle that later will be located at x equals 2, 3, and 1 at time t equals 3. Okay, so this question also a bit macam putar balik sikit lah. Okay. So what the question wants is that, let's say you have this particle at time 0. Okay, dekat time 3, position dia ialah 2, 3, 1. Okay. So at time 2, dia tanya position dia kat mana. So what you have to do is you have to do two things. First, you have to find the original position of this particle. So similar process with question C, cari dia punya original position. Okay, so you find big X. And then after that, use the same motion and substitute time equals to and the original position, okay, and the original point dia berapa to get this, okay, baru patah balik. So dia 2 kali proses. Try later and see whether you get or not. And then question E, plot the deformed shape of a body at time 0, 1, 2, and 3, assuming that it is initially a unit cube. Okay, so yang ni agak susah sikit lah sebab kena lukis. So let's say you have a regular coordinate. So this is x1, x2, and then x3. Okay, so firstly you draw a unit cube. Okay, a unit cube means dia punya length equals 1. Okay, so point here equals 1, point here equals 1, and point here also equals 1. And then label setiap point. Okay. And then what you need to do is you need to find the new position of each point at each time here. So maybe you can make a table to make things easy. Okay, so at time 0, So point A, so coordinate point A ialah 1, 0, 1. Okay, so I give example maybe 1 atau 2 point. Okay, later on you find the others. And then at time equals 1, so you use this equation of motion, substitute the point x and substitute the time to get the new A position. So for example, at x equals 1, so the new position becomes 1 times 0, so you get 1. And at point position number 2, you get 1 as well. And position 3 also equals 1. And then find at time 2 and so on. Okay, sebenarnya ideally ni boleh lukis dengan MATLAB, kena buat code lah. Tapi kalau dalam exam maybe keluar 1 je, 1 point je atau 2 point je. So try to find each of the new position and then try to sketch. Maybe bukan cube lah kalau keluar pun, maybe bentuk bulatan ke. Sebab cube ni dia 3D, nak lukis 3D susah sikit. Okay? Tak dapat nak gambarkan dia punya kedudukan. Mungkin keluar dalam bentuk 2D saja, mungkin bentuk segitiga ke, mungkin bentuk 4 segi ke, bulatan ke, and then dibagi certain points, and then find the new position and redraw the shape. Okay, so similar like last week punya example in lectures. Okay, so try later on you can try exercise number 2. Okay, so your midterm test something similar to this exercise, tapi bukan banyak macam ni lah. Okay, maybe in 2 question. Okay, maybe soalan 1 cari deformation gradient, soalan 2 draw the deformed shape, for example. Okay, now let's move on to our lecture. Okay, so we have the deformation gradient just now that describe the deformation of an object. But the deformation may involve rigid body rotation and translation, and also it can involve stretching, okay, stretch or change in volume. So the deformation gradient can be decomposed, okay, boleh dipecahkan into 2 tensors. So one tensor is the rotation tensor R, and the other tensor is the stretch tensor, either U or V. Okay, so we have tensor U or tensor V. So the deformation gradient F equals R times U or equals V times R. So why we have R times U and V times R? This is depends on which motion happened first, either rotation first or stretching first. Okay, so for the first part here, R times U, this means that U happens first. Okay, stretching berlaku dulu, barulah rotation. So if you look at this figure here, so this is our original position, and we have the final position here. So if R times U, meaning that stretch dulu, baru rotate. Okay, so kita boleh nampak kat sini, the cube is stretched and then rotated. And then for the second part here, V times R means that dia rotate dulu, rotate first. So the cube is rotated first, and then the stretch, baru stretch. Okay, so this is like you want to quantify the deformation and see separately or quantify whether the deformation has rotation or it's just a pure stretching, okay, or pure extension deformation. So we have new terms here. We have the rotation tensor R. So the rotation tensor R is an orthogonal tensor. Okay, so as defined earlier, rotation orthogonal tensor meaning that R times R transpose equals I. Okay, so dia orthogonal. So R is always orthogonal. So ada kegunaan orthogonal ni. And then we have the stretch tensor U. So U is called the right stretch tensor sebab dia duduk belah kanan. Okay, so it's the right stretch tensor, and U is symmetric tensor. Okay, symmetric means that U equals U times T, U transpose. Okay, U equals U transpose. So lastly, we have the stretching V tensor. So V is the left stretch tensor sebab dia duduk belah kiri. So it's a left stretch tensor and it's also symmetric. Okay, V equals V transpose. So semua tensor ni unik. Okay, unik maksudnya dia ada satu je. Setiap deformation dia ada satu je R, dia ada satu je U, dia ada satu je V. Dia tak mungkin ada dua V yang berbeza, ada dua U yang berbeza. Dia tak mungkin. Dia adalah unik. Okay. But this is just a property lah. Okay, it's just a property that explain that for a deformation, the rotation, the stretching are unique. Okay, dia tak boleh ada dua jenis rotation ataupun stretching yang berbeza. Okay, disebabkan we have left stretching tensor and right stretching tensor, we have right stretching U and left stretching V. So we have a new deformation tensor, okay? A new definition of deformation tensor. So we call it the right and left Cauchy-Green deformation tensor. So why we need this? Okay, later on we will see why we need right and left Cauchy-Green deformation tensor. Macam kenapa perlu banyak-banyak definition? Okay, there is some importance with this. Okay, so firstly we look at the right Cauchy-Green deformation. So C is the right Cauchy-Green deformation. So C equals U squared. Okay, so C equals U squared, and it equals F transpose times F. Okay, so this is a formula that you need to cari nanti masa dalam exam, dalam nota. And then the second one is the left Cauchy-Green deformation tensor. So B is the left Cauchy-Green deformation tensor equals V squared and equals F times F transpose. So this is also a formula. So let's say when a question asks you find deformation gradient, so you find F, and then the next question asks you to find left Cauchy-Green tensor. So you know you need to find the transpose and then darabkan F darab F transpose. Okay, semua ni boleh pakai calculator je guna. Okay, tak perlu kira manual. Okay, so now you need to know that there are two new deformation tensor, the right and the left deformation tensor, Cauchy-Green. Okay, Cauchy-Green deformation tensor. So we have why we need this. So we have the tensor U and V that are independent of rotation. So just now we know that the deformation gradient F can be split. Okay, can be decomposed into two tensors, one rotation and one stretch. So now the stretch tensor here is pure stretch. Okay, dia tak ada rotation dalam tu. Okay, so the tensors U and V are independent of rotation R, and it only contains the information about the stretch. Okay, U dan V ni dia describe stretch saja, dia tak ada melibatkan rotation. So why we need to calculate C? Kenapa nak kira C dan kenapa nak kira B? So it's actually easier for softwares like finite element method dan kita jugalah nak kira to kira C, to calculate C, because C you just to calculate Ft times F. But if you want to calculate U, you kena ada square root kat sini. Sebab tadi kita tahu C equals U squared. Okay, and then equals FTF. So if you know only U without finding C, then to find U or to find U through software, then you need to calculate the square root. Okay, bila nak calculate square root ni, we have to go back to calculating the eigenvalues, eigenvectors, diagonalization, back in lecture number 2. Okay, semua ni proses eigenvalue, eigenvectors, diagonalization ni dia makan masa. Okay, pengiraan dia memakan masa dan dia melambatkan proses pengiraan dalam software. Even kita nak kira eigenvalues dan eigenvectors pun macam tergeta-geta. Okay, so that's why they introduce a new tensor C and B, okay, for easier computation. Okay, but in the end, it's important to find the tensor U, okay, but we need to find it differently, okay, in different alternative ways. So now let's look at the stretch ratio, okay. So kita tahu bahawa U and V are the stretches tensor, the stretch tensor. So it's a tensor, meaning that it has nine components. So let's say if you have a square, then kalau dia stretch, maybe dia membesar sikit ke. Okay, the square becomes enlarged. So we want to find berapa banyak ratio dia, okay, berapa banyak dia ratio stretch about this axis. Okay, let's say ratio in this axis, and then the stretch ratio in the y axis. Sometimes dekat lab, let's say lab solid mechanics ke pernah buat ke, bila kita kira strain dekat tensile test, kita kira in one direction punya stretch saja, okay? Strain dekat one direction, kita tak kira in both direction. So kita pull a tensile machine, we're using a tensile machine, so we calculate strain in one direction only. But now for a deformation, we know that it can be stretched in two directions, either x or y position. So to determine the stretch ratio x in the x direction, in the y direction, or in the z direction, or in other direction, dia kena gunakan konsep eigenvalues and eigenvectors. Okay, again, back to lecture number 2. Okay, so this is the definition for finding eigenvalues and eigenvectors. And then lambda here is the eigenvalues or the principal stretches. Okay, in this case, we call it the principal stretches. And R is the eigenvectors or the principal direction of the stretches. Okay. So the important things that I want to point out is that if you use C, the tensor C, so it's basically similar. So C times R equals U squared dot R equals lambda squared R. So the stretch in C is just lambda squared, but stretch in the tensor U is lambda. So if you cannot find tensor U, but you have tensor C, so to find the stretch, you just simply find the eigenvalues and eigenvectors for the tensor C, and then square root this stretch, because this is a scalar value, so dia lagi mudah untuk di square root kan, okay, to find the stretch. So let's look at an example how to apply this Cauchy-Green tensor, the stretch tensor, and so on. Okay, so given below is the deformation, okay, or motion. So firstly, determine the deformation gradient tensor F, and then the right Cauchy-Green tensor C, and then determine the right stretch tensor U and the principal stretches, and lastly, determine the rotation tensor R. Okay, so let's look how the example answer this question. So firstly, we determine the gradient tensor, so using the differentiation formula. Okay, so if you look at this equation, oh, dia tak bagi value time, sorry. Okay, so kita assume this is 0.5 here. Okay, so we assume AT equals 0.5. So to find the deformation gradient, first you differentiate x1, small x1, with respect to all x, all big X. So this is 1, 0.5, and 0. The second row is for small x2. So you get minus 0.5, 1, and 0. And then lastly, it's 0, 0, 1. Okay. So if you do the exercise later, you will find that nak find F ni tak payah tengok formula pun, okay je. Okay. Later I want you to try, okay. So after you find the deformation gradient tensor F, you can find the right Cauchy green tensor. So before that, you need to find the transpose of F. So the F transpose. So ni tak payah calculator lah. Okay, just pusingkan je matrix ni. And then you multiply Ft with F. This one you need to use calculator to multiply. So you get this tensor C. And then the right stretch tensor is just U squared equals C. So U equals square root of C. So because so to find square root of C, you just simply square root all of the diagonal. Okay, but if you have values here or non-diagonal elements, you have values, then you need to find eigenvectors, eigenvalues. So in your exam, you will end up with diagonal elements. Okay, bila you kira ada non-diagonals, maksudnya salah kira lah. Okay, your question will be in diagonal elements jawapan dia. So saya tak adalah gila nak bagi kena cari eigenvalues lagi, mau sejam nak jawab satu soalan. Okay, so you just square root and then you find the stretch, the right stretch tensor U. So the principal stretch basically this the diagonal elements. So this is lambda 1, lambda 2, and lambda 3. So these are the principal stretches, as I said just now, in certain directions. Okay. And then to find the rotation tensor, you need to go back to the decomposition formula. So F equals R times U or V times R. Okay, so we have U, so you can find R. So to find R, you simply find F times inverse of U. Okay, so to inverse U, guna calculator ataupun because this is already in diagonal elements, so you just 1 over each of the diagonal elements. Then you end up rotation. This is the rotation tensor. Then you can check whether this is orthogonal or not. Okay, if you want to make sure that you get it correctly. Okay, so soalan macam ni keluar dalam test. Okay, keluar dalam test dan final. Okay, cari F, cari C ke, cari something else ke, and then you are asked to determine the right stretch tensor and then find the rotation tensor. Okay, soalan dia lebih kurang macam ni. Okay, so later you can try this exercise. Okay, so this is a 2D deformation. It should be easier to compute by hand. Okay, try this later. Okay, so now let's move on to a new definition of strain tensor. So just now we have deformation tensor and stretch tensor. Now we have the strain tensor, barulah strain. So we have deformation, and then we have stretch. So we have deformation and stretch tensor, but we didn't encounter the strain. Okay, So kenapa nak cari strain? Because later on kita akan guna strain untuk determine the stress, okay? The stress in the material, bukan stress dalam belajar, okay? Belajar memang stress lah. So we have the strain tensor now. So the first strain tensor is called the green strain tensor, okay? Strain tensor hijau. Okay, nama orang green tu bukan hijau lah. Okay, dia nama orang. Ataupun we call it the Lagrangian strain tensor. So the definition is simply E, the Lagrangian strain tensor E equals 1/2 of C minus I. So C is your right Cauchy green strain deformation tensor. So I is identity matrix. Okay, so this is just the derivation. Tak penting, okay? Tak tanya, mungkin nanti kau tanya. So in exam, maybe if after you find C, for example, you are asked to find Lagrangian strain tensor. So just use this formula and calculate E, okay? And then we also have the Almansi strain tensor. So Almansi tu pun nama orang, bukan air limau ais ya. So Almansi strain tensor or Eulerian strain tensor. So this is Eulerian pula. Tadi Lagrangian is defined as the symbol. This is symbol nu. So nu equals 1/2 I minus B minus 1. So B is the left Cauchy green. Okay. So sometimes question asks you to find the left Cauchy green tensor and then find Almansi strain tensor. Okay, yang bawah ni just some derivation. Tak penting sekarang, okay? Nanti baru keluar. Okay, so we have two types of strain tensor. Okay, we have the green and the Almansi strain tensors. So these strain tensors are non-linear. Okay, sebab apa dia non-linear? So dalam terms ni we have these terms here. So ni menyebabkan dia non-linear. So when you have non-linear terms, then when you want to plot the graph, dia jadi macam tak boleh nak plot dia linear graph lah, lebih kurang macam tu lah lebih kurang. So if we assume that the displacement of the material is very very small, then we can eliminate the non-linear terms. Okay, we can eliminate the non-linear terms. Then when the non-linear terms are eliminated, then we have a new strain tensor. Okay, so we call it the infinitesimal strain tensor or the linear strain tensor. So this linear strain tensor is the strain tensor that you usually use masa dalam solid mechanics. Okay, masa dalam subject solid mechanics, SOM 1 and SOM 2, or when you do the tensile test. Okay, we use the infinitesimal strain tensor. So basically, the green and Almansi strain tensors are material yang deform dengan sangat banyaknya. Okay? That causes the displacement of the material to be quite large that you cannot assume to be zero. Okay, so this is the infinitesimal strain tensor. They depends on the displacement. So it doesn't depends on the term C, B, and so on. Okay, they depends on the displacement. Okay. So before that, if you look at the definition of green strain tensor, so the first part here also the formula. Okay, you can define strain tensor for green strain tensor in terms of F, the deformation gradient, and for the Almansi strain tensor also you can define in terms of deformation gradient. Okay. Okay, terlalu banyak definition. It's okay. Kalau soalan keluar, just refer lecture notes. Okay. Semua ada dalam ni. Okay. So lastly is, I think this is the last one. Okay. So the last part is the velocity gradient. Okay. Ataupun we call it the rate of strain tensor. Okay, the strain tensor can also be defined in terms of the rate. Okay, kadar perubahan strain. So this is a physical quantity that describes the rate of rate of change of deformation of material at a point at a certain moment of time. So the velocity gradient, so tensor L, is defined as the spatial gradient of velocity vector. So L is just the gradient of the spatial vector or Eulerian velocity, sorry. So if you define L in terms of the deformation gradient, it's simply this, okay? Or Arbekan deformation, we get F dot equals LF, okay? So why we need L? Why we need to calculate L? Okay, so usually we calculate L, the strain rate, if you do CFD, okay? If you do CFD simulations. For example, siapa yang buat CFD simulation in FYP or take CFD subject, I think you will encounter the terms rate of strain, okay? Or strain rate, okay? So this is the strain rate, okay? Or the velocity gradient. Okay, when we calculate the velocity gradient, then we can determine or decompose the velocity gradient into two metrics, okay, or two tensors. So first tensor, we call it the symmetric rate of deformation. Okay, so this is the symmetric rate of deformation. And then we also have the skew symmetric vorticity tensor. So this is vorticity. So we have rate of deformation and vorticity tensor. So the formula is this. Okay, so sometimes when you do CFD, kita nak kira vortex, okay, vortex in a CFD simulation. So basically, if you want to calculate vortex, is to find this vorticity tensor, okay, in your software. Okay, so to find the vorticity tensor, then you need to use the velocity gradient tensor. Okay, sometimes software dia tak kira kan vorticity, kena kira sendiri. So you kena kira strain rate, barulah kira vorticity. Okay, sometimes a software already have this formula in the software given. Okay. So I think this is the last exercise. So I think for the question A and B, you can try find it yourself, okay, using the formula left and right Cauchy deformation tensor, and then the strain tensors. So let's do question C. So I want to demonstrate to you how to find the velocity gradient and the vorticity. Sebab keluar midterm lah, okay. So velocity gradient and the vorticity. So firstly, let's write the formula. Okay, so the vorticity is basically the velocity gradient is basically you differentiate v over del x. Okay. So firstly, you need to find v1, the big V. So v1 is basically you differentiate x1 over big T, the small t, sorry, small x1 over t. So you get 2t x2 squared, and then v2. So this is big V, okay. You get t, sorry, you get x1 squared, and then big V3, you did. And then to find small v, you need to substitute the inverse, okay, x1, x2, the big x1, big x2, and big x3. Okay, cari inverse dia. Okay, macam susah je. So you need to find the inverse. Okay, so if you rearrange in matrix, okay, sebab dia ada x square. Okay, soalan ni macam lain macam sikit lah. It's okay. Kita abaikan soalan ni. Later I will give you one example, one exercise for you to do it yourself. Okay. So when you want to find V1, V2, and V3, you need to substitute the inverse. Okay. Substitute x1, big x1, big x2, big x3 into this, so that you get small v1 in terms of only x1, small x2, and small x3, so that you can differentiate them. Okay. Okay, unfortunately soalan ni dia lain macam sikit. Okay. Later on I will give you an example, a different exercise. You try yourself. Okay. And dah try, bolehlah show kat saya nak check ke. Okay. And that's it. Okay. I think that's it. Tak ada dah. Okay, so dalam topik ni there are a lot of terms yang baru lah, tak pernah jumpa lagi, yang mungkin macam mengelirukan, tapi our exam is open book, so you can just refer your notes. Mungkin ada satu dua pengiraan yang sedikit tricky, yang kena macam tadi inverse kan, motion. Try to understand the process of calculation, so that during exam tak pening kepala lah. Okay. So I think that's it for lecture. I just want to explain about your test next week. Okay. So your test is next week, week 7. So test midterm, mid test consists of 20% of your overall marks. So there will be 4 questions. So 4 questions, 40 marks. Okay. So question 1 will be about either lecture 1, lecture 2, okay, lecture 1 and lecture 2, about vector and matrix. Okay. Okay, about vector and matrix. So lecture 3 about calculus, tak tanya masa midterm. Okay, dia tanya masa final nanti. And then question 2, I think is about sketch the deform shape. Okay, saya tak berapa ingat, tapi you have to sketch a deform shape. So you need to know how to find the new position and then sketch, okay, dalam kertas lah. Okay, so you can try exercise from last week lecture, okay, lecture 3A. And then question 3 is about finding F, C, R, U. Okay, so like in this lecture. And then question number 4 is about finding what we learned just now, the velocity gradient, and then the rate of deformation and the vorticity. Okay, so 20%. So your time for midterm is actually 2 hours. So 2 hours, exam ni sejam setengah. And the remaining 30 minutes is for submission. Okay, so what I did usually untuk subjek yang sebelum ni, you need to submit within this time. Okay, so if you submit 1 minute late, I deduct 10 markah. Okay, so please submit within the 30 minutes. So soalan ni simple, you don't have to calculate manually. Okay, kalau ada software MATLAB ke, guna MATLAB tak apa, tapi please show some important steps lah. For example, like let's say to find C equals FTF. Okay, this is you need to show. Okay, if you tak show, hilanglah 1 markah. Okay, don't simply write C equals the matrix. Okay, so just show C FTF, and then maybe you show what is FT, and then calculate C FTF. Okay, you can use calculator, but you don't have to show like detailed calculation yang terlalu detail. Okay, if you have MATLAB, boleh guna MATLAB. So that's why 1 hour 30 minutes is I think enough. Okay, and submission within 30 minutes, 1 minute late minus 10 marks. Okay, yang ni for real. Okay, siapa yang pernah ambil subjek dengan saya, this is real. Okay, tak main-main. Okay, walaupun bulan puasa. Okay, so that's it for today's class. If you have any question, you can WhatsApp me later, and see you again in week 8. Okay, before Hari Raya. Okay, before Hari Raya in the following week. Okay, so that's all for today. Assalamualaikum and goodbye.